of a battery here. And first of all, just because of our convention, I'm going to call this electrode what? A. A. Like this. Going to be goes from point A to B. If this is 1, this is 2, let's suppose this is going to be conductive compared to that. So we're looking for a conductive body. Then how's the current going to flow? Yeah, so flow lines are going to kind of concentrate in like that. They're going to get sucked in, right? Now, what happens, what's going to happen on this kind of squiggly boundary? What actually is going to happen on this boundary?
Negative charge is left.
I'm going to get a charge, right? And the reason I get that charge is the fundamental reason was that J, the current density, on if this is unit 1, this is unit 2, that J, the normal component of the current density always has to be continuous. That's just so that it's steady state. And then this was the current density here is sigma 1 E1. That means sigma 2 E2 and if the conductivity is changing, that means that the electric fields are changing. The only way I can get an electric field to change is if there's a charge on the boundary. So that means every time you got current going through anything, there's charge there. Now, then the only thing is, okay, well, which way is the charge, or what is the sign of the charge? And there was a formula, I guess sigma 1, sigma 2, 1 times E1, E primary. So whatever the primary field would have been, then there's a charge is filled up. So if sigma 1 is less than sigma 2, then this is less than 1, this becomes negative. So then all that becomes negative. If we had reversed these guys, then we'd have a positive charge, and that current would repel the currents, and then they go around like that. Okay? That's the excitation of the body. So that's the first part. But now we actually want to detect that. So we're going to set up a measurement. So we're going to measure the electric potential. And we actually had symbols for those guys. What were they? M would be the positive part of the potentiometer. And you actually have to be careful of this if you're working with these in practice. Sometimes in the field, they switch the polarities. It's really easy to just change the wires. And then you get data with the wrong sign. And it's like, polarities in electromagnetics is no different than polarities in seismic, right? Look at the trouble you have trying to figure out what's the polarity of my seismic data. Okay, so we have that. Then we had a formula that allowed us to go from whatever voltage that we had measured. Okay, so that resistivity, I can't remember, I/V upon G, I think that's right. Anyway, so this was the apparent resistivity. The point was that for any, and G, is made up of 1 over RAM minus 1 over RAN. So it's just made up of these geometric distances between each current electrode and each potential electrode. So that allowed us to convert a field measurement to at least something that's got the right units. It's got resistivity. And we found that we could do a survey using different types of geometries. There's a whole bunch of ways that we could have these guys orientated. So we could have them, let's say this one here would be a dipole. And remember, now we decided, okay, we're going to plot these things. So we're going to try plotting them on the page. We'll just, for each separation of transmitter and receiver, we'll just plot things at 45 degrees, and then we get an apparent resistivity from the formula, and we just plot it right here. And then we keep moving these things around, and eventually we get something, what was that called? The pseudo section. That's a word that you'll hear a lot, marine, for people doing the marine EM. Data will be plotted in pseudo sections. So that's a portrayal of the data. You can't make any, in general, you can't make a geologic description from that. For that, you need to invert the data. And that inversion of the data then takes you back to something. So this has got, this is true lateral distance over here, and this is just some pseudo depth. And usually it's often related. So if this is A, and this is A, and this distance here is NA, then sometimes they'll just have numbers down here like 1, 2, 3, 4, which just tells how many spacings you are away. So you'll probably see that. Then we take these data, which is just a map of the data, and we convert them to something that is in a true XZ plane, and it's really plotting rho as a function of the X and Z. So this is now a physical property model that you can take a look at, and for this you can make geologic determinations, not the data. We showed examples of how this would work in 2D. That's actually very, very nice. So in 2D, if I've got some kind of layered structure and maybe a target in here that's going into and out of the body. So this is Z and this is X. If I'm going to do an experiment, then what's the geometry that I'm going to collect the data? Should I just sort of collect the data like right over the top and go in and out of the board, or do I go across? Across. 2D structures, you always go perpendicular to the structure to collect the data. In 3D, 3D is simply more complicated, and you don't know what shape the target is. We actually talked a lot, or we talked somewhat yesterday about the whole concept of coupling. So if this is a narrow target, something that looks like this, if it's sitting in here, there's going to be currents that are going to flow. So there's a coupling there. But if I change the orientation of this target, make it kind of flat, then it couples differently with that primary field, and a different answer out. Whether you can see a particular target, or what the orientation is, or what your what particular combination of transmitters and receivers you have, you actually have to do numerical modeling in general to see, like, okay, can I see this or not? Is this a good combination? There's no real magic answers to these things, as is true in lots of problems. Oh, yeah. I'm on. Thank you. So then we introduced the apps. How many people had a chance last night to use any of the apps?
I tested one example. Yeah, I have an example to yes, make a question.
Oh,
Yes,
okay.
I tried this. I was testing like reciprocity.
Yeah.
To see, and I made an example like the monopole dipole.
Yeah.
So I put yes monopole dipole, and then I changed this dipole for this point with the same middle point, and this point to here with a cylinder. Okay, and after in this case, you have an asymmetry, and the results are different if I put like 2, 1, or 1 and 2.
Oh, so, but, okay, go ahead.
Yes, I was thinking about, okay, if I'm doing a measurement to build this pseudo section. Okay, I'm moving the dipole all around, and I move the source, the monopole all around. So by this construction of this 45 degree, for the same points, whether I have this measurement, or while I'm moving, I have this measurement, for the same points, I would have like 2 different values to put in my pseudo section. So it would not have a unique definition because I have 2 values for the same single point.
The reciprocity strictly holds if you've got, let's say, a current source here and measuring the potential.
Yes, 1 to 1.
1 to 1. Or if you have a dipole
And a dipole.
and a dipole.
Yeah.
Okay. Because then you're always, the thing is you're always injecting potential or you're injecting current at the same location, or you're using the same electrode locations to measure the potential. So under those conditions, you should have reciprocity. If you do not have reciprocity with the...
I fully agree. That's why I test the situation, and okay, it's agree as expected.
Okay.
So physics is right. But the point, my question is not, I was expecting that when I have 2, 1, and then I move like 2, 1, I would have different results. So it's okay to have different results.
All right.
But my question is, if that's so, the pseudo section convention of construction, by what I understand, has a fail because I have 2 different values for the same experiment. I'm just moving and moving, and for the same points in the pseudo section, I have 2 different values. So it's not uniquely defined. So mathematically, it's not consistent. If you allow me to say.
But that's a way of visualization.
So you need, in this pseudo section, you need to put an additional convention, like, okay, I always have the monopole in the right side of the pole. Otherwise, you have 2 different values for the same pseudo section points. Yeah,
I should bring up the pseudo section.
Or the case history.
Yeah.
Actually, I have. It's easy to project. I have 2, just 2 PowerPoints that I.
Oh, okay. Sure, yeah, that'd be great. Wow, good for you. Yep. Yeah. Or can you?
Yeah, that's right.
They have a VGA.
Yeah, I have a
No, it's HDMI. There was one.
There's a VGA.
Well, here it is, here it is.
Yeah, that's not the. Do you have HDMI?
I have the springboard. Oh, yes.
You have HDMI? Let's do HDMI.
No, I don't have. I have the springboard. I think.
Yeah.
No,
I have
HDMI.
Oh, do you have HDMI?
Yeah, I think that if you pull up on ISO, that would be
Helpful. Because we plot the full dipole and dipole pole separately.
Oh, okay. On the synthetic.
Or on the.
No, field data.
Right.
Let's see.
If you like what we can do, I've got a USB and you can pop it on there into Doug's computer. Yeah, so if that doesn't work, feel free to just put it on here and put it on.
Yeah, we just try this one. Are the words? Yeah, it seems like, yeah, it's not getting.
Degree screen share. Sorry, Doug, can I
That's
check
fine.
first?
This guy going.
I'm sorry, I'm just gonna re-screen share. And then Doug, unplug this guy just so that he can plug in his USB.
Lindsay, can you plug the HDMI in the better?
Okay, that's it.
Hey, thanks. Can you try it in the wall, Soggy? Or Doug? I think the HDMI is loose in the wall. And then which one is it? The one that's not mine. There we go.
Yeah, that's. And just this slide. Okay, that's it. So that's the parameters that I set. I put in the upper left corner. So yeah, it's almost self-explanatory. So I did, let's look at this bottom right picture here. So that's the A and B, and the point M. So the points in the pseudo section, that's row with this value, 138. So I just keep doing the experiment. So I move the A and B and the M. So if you go to the next slide.
Oh.
Okay, so that's it. I will just keep doing the same experiment. So afterwards, the A and B. Oh, yeah, that's it. So the A and B is there, the point M is there, and they have the same points in this pseudo section space.
Yeah.
But it's a different value.
Yes.
So which one would I put in the pseudo section?
Oh, you have two pseudo sections.
So I have like
I see.
experiments.
Yeah.
I will build one subsection with the point in the right corner and another subsection.
So sometimes we call dipole pole or pole dipole, like that way.
If it's in the left and the right.
Yeah, just
so we
That's
put
kind of very typical in mining.
Just a sec, hold on. Oops, where am I?
Oh, if you have tried the pole source, like the other one was dipole,
Yeah.
and the receiver was pole, and now you change that actually, like use a pole
Back
source
to DC.
and the
And
dipole receiver.
So I will
Then it's supposed to be
recover the reciprocity.
and yeah, that's it's reciprocal.
Yeah, that's it.
So you've tried it's not quite reciprocal. You know, sometimes that's actually a good sign. Like oh, you got something. Like let's say you have just one D layer, it's going to be exact same, right? But let's say you got a different structure, a 3D structure, 3D structure. It's different. Oh, they're probably something going on. So yeah, even just for QC standpoint, it's
Yeah,
actually
we'll just get to the.
it's okay. Oh, you
Mount
take two different images. Right? Oh, okay, I think I probably have something different on this side, that side. then now that's the time, oh, I need to invert to get a one.
To see, yeah, the actual structure.
It is actually quite remarkable, this reciprocity. Oh, okay, so here to first answer your question. So if we, what we see here is the Mount Isa data, okay, going across here, and this is pole dipole. Okay? So each of these has got, like here's our pseudo section. So it looks like this, right?
Okay.
Okay, now if I do the other way, okay, so I use these potentials on the right with the current on the left, I get that. So they can actually be very different. So I got two different pseudo sections. That's just like two maps of data. That's why I was saying yesterday that we have 20 maps of data. We've got to convert those to one conductivity. But the thing that you mentioned is, I mean, it's really interesting and it's totally unintuitive, but it's physically always correct, and that is with the reciprocity. So imagine this, okay? Just kind of think about this. So from our understanding of excitation. So let's suppose I put a current here, okay? So I put a current here, and you know what's going to happen. I'm going to get all these concentrated negative charges here and positive charges here, right? And then I'm way over here, and I'm going to measure the potential. Okay, so it's now the distribution of that guy there. Okay. And I'm going to get out a particular voltage. That turns out to be the same. If I do the same thing here, and now I put the current over here, imagine how different the charges are. Like they're way different, right? So I got now some broad kind of negative charges sort of sitting around that whole side, right? It's just completely different situation. And I got a few positives here. And I'll be darned if you don't get the same potential out of it. I mean, I never cease to be kind of astounded at some of the things that come out of mathematical and physical reciprocity. Anyway, that was good. So gold star for thinking about what we did. Okay, so were there any other things that came up in DC resistivity? Yes.
Just a quick question. So, but in this case, if the location of the current and the measurement are perfectly symmetric with respect to the sphere, then we'll get exactly the same measurement.
Well, you get the same measurement anyway. It doesn't matter.
In this case. In this case, in the case that you drew on the whiteboard,
yeah,
we'll get two different values.
No, you will get exactly the same value. That's what's astounding about it. Right? It's just totally unintuitive. Right? Yeah. Like I put something. Like it could be. Right? I could put a current right in here. Right? There's no reason it has to be on the surface. So now I put a current in here. Okay? So here's my current. Here's my electron. And now what I'm going to get is strong negative charges there and positive. And I get a potential here, right? Because I just sort of sum up all the Q's over R squared, right? And now I contrast that with this, putting this as a current electrode, and now I'm going to put my potential electrode right here. So all of these charges are going to be, lots of negatives here, and then some positive. And now I'm going to put my potential electrode there, and I'm going to get exactly the same number. Yeah. by sentence entirely. Okay. So anything else about DC resistivity? What we did was, well, we looked at a couple of case histories, and basically we showed that, whether it was for perhaps monitoring for steam or monitoring for anything else, and as long as you got a change in conductivity, and actually it would come back, Marcus, to the point that we made yesterday. These things are complicated, right? There's a lot of different reactions that can go on. If you put steam in, then it depends on your host material, how the temperature effects are, what's dissolving out, and it is simply not trivial at all. And this is where there's a lot of work that needs to be done with rock physics, laboratory measurements, and really understanding what is the relationship between a change of parameters and that final conductivity. That kind of came back to Tiantian's comment yesterday too. At this point, what we're trying to do is to show that we could actually do a survey and get a change and observe a change in that electrical resistivity, translating that to something that you want to know with respect to monitoring or anything like that. That's another issue. The first important thing is like, okay, I've got some signal here. Something is changing. So now what do I do? The note that we left this on late yesterday morning was that we had a sphere in a kind of a target, and we said, okay, well, if I put in something that looks like this, so I've got Electrode, the Electrode. I can measure if I just went across here with an M and N and kind of move those across here. So that would be my sort of gradient survey, and then I'd find if this was 500 and this was 1, I'd find out that my apparent resistivities, I'm just going to profile like that, kind of look like this. Right, so so this is rho on this axis. So I got a resistivity low here, and actually it was a little bit of a high on here, but we kind of understand that those numbers here just because of our relative locations of our potential electrodes to where the currents are. The thing that was a major consequence here is like, okay, what happens if we put in a layer? Okay. And now we can make that layer resistive or conductive. If we make it resistive, then as we saw yesterday, the current cannot go through. The current for a resistive layer just has to kind of get funneled up like this. So all of the currents go from A to B, and they're all trapped. In other words, this acts as a screen, and it doesn't have to be thick. It just has to be resistive. And this is why I don't know whether petrobras would do you ever have any kind of tailings ponds or ponds that you need to keep contaminated water or something like that? Mining industries, of course, always do. Sometimes in frac projects, you need to store something. And so under those cases, sometimes you can put in a liner, so like polyethylene liner or something. It's got really high resistivity. And yeah, that means that current doesn't go through. So that background conductivity can play a real role. If it's a resistor, just shunts keeps the current up. If it's a conductor, then all the currents, instead of staying up in the top, actually just get sucked down. Just general principle that current likes to travel the paths of high conductance, and then it comes back here. Either way, if you've got a body underneath here, you're basically screened. That opens up the door to, like, what else can we do? And that was where we kind of were yesterday, and starting with EM fundamentals. So, oops, I'll give you your. Oh, it's yours. We're, stage 2. It's National Tequila Day. So whatever happened? My God, how did we get started on pseudo sections when we talk National Tequila Day? Okay, so who's going to enlighten us about National Tequila Day? What it is, what we're supposed to do?
Okay, tequila.
Oh, wow.
Is it
PowerPoint?
Shame on you.
And this is all courtesy of Petrograph, right? Okay, yeah.
So we have some options here. We have Henderson Heights, we have Capital Bar Midtown, and we have a bar called Pistoleros.
Pistol?
Pistoleros.
Pistol or Pisco?
Gunners.
Oh, Pisco. I'm Canadian. We don't have guns. Okay, and so is there like a protocol, or is there something that we're supposed to do, or do we just go and
Just drink tequila.
just drink tequila and get totally correct?
Generally, the best place to go is in Washington Avenue. It's the best bars.
Yeah, so
Washington
So
Avenue.
Henderson Heights is close to Washington
So-
Avenue.
Maybe this one is the better.
And then what is, in your opinion, the perfect tequila ingredients?
Tequila?
Tequila, salt, and lemon. That's
Salt and lime.
Yes.
So no triple sec, or how about a margarita then?
Margarita. Okay.
Okay, so basically just tequila, lime, a bit of salt.
Yes.
That's
One shot.
one shot.
Yes.
Just
And then loop repeats.
I look repeats.
For I equals 1 to 100, it repeats.
I like the way you think. I like
Four. It's a 4.
It's four loops. Oh, good. Okay, well, thank you for that. Okay, so fundamentals. So again, the reason that we want to consider something else is that we can have really large areas, or different. Sometimes you just can't do DC resistivity, right? So here's the basic experiment, right? So we've got a transmitter. Somehow we're going to fly this one. And that transmitter is going to give rise to a magnetic field. So everything depends upon the current source in the transmitter. Right? So if the current source is like this, so this is I, this is T, and the current source is that, and then shuts off, then we have an on time and an off time, and we can measure stuff that's in here. If the current source is, so this is often called a time domain, yeah? And if the current source is harmonic, then we have a frequency domain. Yeah? We just have a time source. So we have a time-varying magnetic field, so it's either this way, that gives a short time, or continuum, whatever. Time-varying magnetic field induces currents in conductors, and those currents give rise to magnetic fields that you could have at a receiver. So very simple experiment. Yeah. We talked about the magnetic field. We get a little sloppy when we talk about B and H. We often refer to both of them as fields, but B is really a flux density, and it is circular around a wire, so it's your right-hand rule. It's given by Ampere's law. And the important thing to really remember again is that if I take a wire and I loop it around, then it's going to give a magnetic field that actually looks just like a bar magnet, with the strength of the magnet being the called the dipole moment, product of the current and the area, and everything falls off as 1 over r cubed. So we're going to see this a lot, because that really emulates what is going on in an airborne survey. That's a good word. And also, it's just a generic way of understanding how to look at fields. So the main thing was Faraday's law. And again, it's probably worthwhile just doing this. So you remember the experiment? We've got a magnet and got a coil that's hooked up to light bulb, and then we can measure the voltage, and we can also measure the which direction the current is in. So this was probably one of the more fundamental things. First of all, we need to define the total flux. And the flux is just the area integral of the normal component of B crossing that. So it's that gives you the flux, and then you get a voltage into, just consider a current circuit for a second, with an R and an L. And the voltage or EMF that's induced in that is dependent upon the time rate of change of that flux and a minus sign. The minus sign was Lenz's law, and it always tells you then which way the currents are going, because the currents have to go in such a manner as to oppose the change. So that's an important thing, because we use that time and time again. We're always trying to think, okay, where's the flux coming, and now how's the current going to go to oppose that? If I move the magnet in, flux increases, but the minus sign means I've got current going in the negative direction around the circuit. If I change, well, the other way, the current now reverses. It goes in that positive way. So if I move the magnet in and out, then the current in the loop is going jump, 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 jump. And we had 2 apps for Faraday's law. The first was for time domain, and then we also had one for frequency domain. And I introduced a simple example, just using 2 coils. So there's a primary current, it's so that's the red coil, and we've got a target coil inside, and the target is going to be denoted by an R and an L. So for those people who do circuit theory, R and L is fine. For people who don't do circuit theory, it's not really that important, because we're not going to use these notations as we go later on. I'm just trying to get you a physical understanding of what's going on. So Jaja, yesterday you were kind of concerned, like, oh, worried about circuit theory and things like that. But
That's just mine.
Yeah, it's just this is just a way of helping us out a little bit, and I'm going to show you in a second that by thinking in terms of these loops, you can actually go quite a ways to understanding what the character of fields are going to be. So it's very useful. If we turn the, so if we have this example here where the primary field is just a constant, then the magnetic flux is a constant. The moment that we turn the current off, then now there's no flux. So it goes to 0. So that means there is a huge time rate of change. In fact, it's like a delta function, it's infinite. That immediately sets up a current in here. So it's immediately I get a current, and it has got a strength IS. And then that current decays with time, and in this case for the circuit, it depends, that time decay is L upon R. So that's our way of working with things. And then we're going to work with something called the response function. And that is really telling us, like, how are things changing in time? And it's e to the minus t upon tau, which if you plot it in linear form, looks like that. If you plot it in log form, it looks like that. So that's basically what happens in the time domain. I showed you an app yesterday. Yes?
So basically, the y-axis you're showing is the response function. So if t equals to 0, they all should start from 1. Like those 3 lines, like the red ones, actually start from 100 when t equals to 0. Response function in the chart.
So I think that's the derivative of the. So I think it's sensitivity t. So that's for b, q. I think yeah, that's for. Impulse function. This is a step function, so yeah. So it's wrong.
Sorry, which one's DBT?
The plot is DBT, I guess.
Yeah, maybe you have this 1 over tau. You have a tau factor in the.
Yeah, so I think it's wrong. So sorry.
So it's not response function.
Okay, oops. I never noticed that.
Yeah. So, but actually what you measure in time domain is the time derivative of b. So if you're right. So if there was b, it's actually start from 1 and then decay differently.
Okay.
But the actual function, what you measure is the dBdt, which is kind of time derivative of q. So if you take the derivative, you're going to get the tau on tau. Then depends upon tau, you're going to get different starting point. That's what is plotted. Sorry about that.
Yeah. Whoops. That's interesting. You know, we've shown this, and it's never really caught anybody's sense. You actually should also get a star. We keep forgetting these things. Yeah, because we're always measuring things with a 3-loop system. So now you get a B field that's coming up, but you actually don't measure B. You measure dB dt because you're measuring it with a column. So okay, we will straighten that out. Thank you. Okay, so that's what happens with a time system. But here, we could also have a different transmitter. We could have harmonic. So nothing really changes. The physics is exactly the same, but the difference is that in a harmonic system, the primary is always on. So it never goes off entirely. And we're left in a situation that there has to be a current induced in the in that target, but it's going to be a bit more complicated. The one thing that we do know is that it has to vary as cosine omega t. If the primary is cosine omega t, then current in the target has to do that. So if something in the target is varying current is cosine omega t, then really the only thing that can happen is that you're changing its phase. So it's really an amplitude and phase. And so that's what this is indicating. The current in the target has got some amplitude, and then it's phase shifted by an amount of psi. And then if we break that up into 2 parts, we simply see that there's a part here that's pre-multiplying the cosine, and we just call it in phase, and sometimes we call it real. And the other part, which is sine, we call it out of phase, or we call it quadrature, or we call it imaginary. The reason for those is that mathematically you always treat these as e to the I omega t, so that's got cosine plus I sine, and then you've got a real and imaginary part. So that part all kind of comes from the fact that mathematically we're just so used to working in complex exponentials. There is a formula for the phase height, which is pi upon 2 plus this. And so this quantity here is really the combination of values. and it's something that really determines what the response is like, and it's called the induction number. So the induction number increases as frequency increases. It increases as R decreases, and it increases as L. We're not going to be think too much about L, but these are the two things that you want to think about. So if you're operating at a very high frequency and you've got a big conductor, then the induction number is really big. And sometimes they'll even call that, like your response is at the inductive limit. And physically what's going to happen is all the currents are just going to be wrapping around the outside of that body. On the other hand, as omega goes to 0, you get to more the resistive limit, where it's sort of controlled by low frequencies and resistance. So we tend to plot the secondary fields that come up as both that in phase and the quadrature phase. And they'll both look like that. And the only question is, like, who's bigger at any given time? If I'm going to take a measurement, is there more kind of signal in the in phase or in the out of phase parts, or vice versa? All of that is codified by this response function, which plots the response as a function of the induction number. And if we look at, so basically, that plot is just coming from, let's just evaluate this for any particular induction number, and then we, see what that amplitude is, see what that amplitude is, and then that gives us these guys. As a function of induction number, the real part follows this curve here, it's the dark line, and the imaginary part follows this line. So if you're doing an experiment, perhaps this is where we got a little bit confused yesterday, but it was 4:30 in the afternoon, so let's give us a break. When we do the experiment, we're doing it only at one frequency. Okay, so doing it at a frequency. So that would put us at a particular induction number. And in this case here, if we happen to be here, then the real part we see is less than the imaginary. So most of my response or the bigger part is going to be in the imaginary component. And this is going to be a little bit. The other way of working with these complex numbers, and sometimes we see that in the marine, in the CSEM case for the Barents Sea, I'm going to show you their signal, and that is actually plotted in terms of the amplitude and the phase. And it turns out that the information is more visible when you actually look at the phase. So either way, it's a complex number, amplitude, phase, real imaginary part. And then we have the two harmonic gap for this, which just allows you to kind of change the parameters and just to see how the information comes into this real or imaginary. Okay. So at this point, we're kind of partway through the process. So we've gone from a transmitter to a target, and we've set up currents in the target, and we've got some idea how they behave. Okay? In the time domain, how they're going to decay. In the frequency domain, the two parts, that part that's sort of in phase. So we've kind of done the excitation part. Good. So the next part is, and actually in conjunction with that, you can see there's no difference in the physics of what's going on. Both of them follow Faraday's law, and then they generate magnetic fields with the Ampere's law. Okay, so the next thing is to put it together and then have a system that actually has a sensor to it. So we're going to take a look at now the fields that come from these currents in here, and going to measure them up here. Now we have some have some options. You're going to measure the magnetic field. You can do that directly. There are instruments out there. They're called flux gate magnetometers. And they can measure the three components of the field. Very often, these are used, if you have magnetic observatories or something, they will use these flux gate magnetometers. For most of the work that's currently done in geophysics, at least for mineral exploration, or even for your ocean bottom stuff too, again, you use coils. And so if you have a coil, then you're measuring dB/dt. So for these, you can have a single coil, or you can have coils in multiple orientations. And yeah, so that's basically it. Measure B, measure dB/dt. You have a single component, you can have three. I want to come back to this issue of coupling. So let's first of all think, and we kind of did this a little bit yesterday. So remember, so we had let's say a transmitter coil like this, and then the magnetic field comes around that looks like this. So if you're sitting in a position like right underneath, then really you've got perfect coupling, because the magnetic flux from here is just going all the way through. If you start to orientate your body, I did that yesterday by looking at this guy, and then I started to tilt him, and then we looked to see how much flux was coming through and what the strength of the currents were, and you can see that was decreasing. If you get to a point where that primary field is just simply parallel to the plane of your receiver, you don't have anything. There's no coupling here at all. So the relative orientation of your target to your transmitter, to its primary field, really determines how much flux is coming through. So that works for a transmitter and a receiver, but there's also, you can think about, oh, well, maybe that transmitter, maybe those are currents in the target, and this is my receiver. So another double set of coils, and then depending upon what where your receiver is compared to the fields from your target, now you're either well coupled or not coupled. Okay, so this is now also a very important point, that you're going to measure something with a coil, and depending upon the orientation of that coil, you might get a big signal or a very weak signal, just how everything's coupled. Okay? So now we're actually ready to put it all together. When we look at the at our signal that we're going to measure, okay, we're going to have both a primary and a secondary signal. And what we'd really like to do is just be able to have a ratio of, okay, what's the ratio of our secondary magnetic field to the primary magnetic field? So here we have it here. Here's our transmitter, okay? And it's going to give out magnetic fields, and we can measure them at a receiver, let's say out here. Those fields also go down into here. They measure they produce currents in here. Those currents produce a secondary field that could be obtained up in here. So we can replace this system now by 3 coils. We have a loop transmitter, we've got a loop target body, and we've got a loop for a receiver. Okay. So this is sort of the real situation. This is how we're going to think about it because of the use of our coils. An important thing here is that coupling that I always talked about, or we've been talking about, and it's it's called a coupling coefficient. So the coupling between this loop and that one is M12, and it's just geometry. And we can see that that's what was happening. It just kind of depends how one thing was oriented compared to the other. So that's given by this thing here. So that's just geometry. You can evaluate that. And similarly, the mutual coupling between M2, 3, body 2, body 3, is given by this. And we can also get this coupling. Okay, so just by geometry, we know what these coupling coefficients are. Good. Now we're all set up. The thing that we're wanting to measure, or the thing that we can measure, is the voltage from the primary field and the voltage that's coming from the target. That ratio is actually, because both of them are happening on the same manner in the receiver, that's really the ratio of the secondary magnetic field divided by the primary. So that's the thing that we're interested in, like how much of a signal are we actually getting out from that? And the thing about this is that although this tends to look maybe a little bit complicated, it's actually, you could almost have written this down just because of what we now understand. I think that's kind of nice, because this is a bit of a complicated formula, but we have enough information, we just almost write it down. So let's think about this. So let's look at the secondary field. So the secondary field is information that's gone from here to here. So that's got to be there has to be an M12 in there to take account of that coupling. And then it goes from here to here, so that's an M23. So these are the two kind of coupling coefficients, right? And then there's some interaction, at the target that actually gives a response, and that's what this guy here is. Here's your response. Here's your response function. So HS is really the two coupling things and a response. Okay. The primary is just the information that's gone from here to here, and that's basically M13. So all of this sort of physical understanding kind of comes into this particular formula, and so you can see that the strength, the ratio of the target to the primary, is given by coupling coefficients times the response of the.
Just to clarify, both these fields are measured in the loop tree, right?
Correct.
It's just the ratio between the one you created and the one that goes through the.
Correct.
Okay.
Yeah.
Okay.
So that gives us now the ratio of the secondary to the primary field. So that's a good number, and this Q here, that's really our response function. So that's got that in phase and quadrature phase. This guy here goes out. Okay, so now we have this 3-loop system, which turns out to be very valuable in kind of understanding, at least at the first order approximation, what you're going to get out from a particular system.
I have a question. So
Yeah.
how do you separate the secondary from the primary? Because you only use one loop to have it.
Right, we'll come to that, but that is a perennial problem, so people have to address that. So let's just take a look at what is going to happen here. Now what I'm going to do is so imagine we got this body, okay, and we're going to use an instrument. Actually, this is a very common instrument. It's used a lot in environmental geophysics, and it's basically a loop transmitter and another loop for a receiver. It's held on a fixed coil or on a fixed rod, and it operates at only a single frequency. And you strap it on, and you just sort of walk across like this. When you do that, each time I'm here, so again, if I can use Sergio as our target, if here's my transmitted coil, then it's going to induce some currents in you, and I can pick them up on the receiver. Okay, so I'm going to get something. Now do it here, I'm inducing a different, receiving a different, So I'm going to get some kind of a signal. The signal I'm going to get actually looks like this guy. It's a typical signal, and it's got a lot of character to it. But I want us to kind of walk through and just understand, like, okay, how do we get this guy, and what's really happening? So let's just take it piece by piece, and let's suppose that we're sitting over here at point A. So we're over here. So again, you need to decide how you're going to geographically locate your instrument with UTM. And we're going to say, well, in the middle of our instrument, that's kind of where we're going to say our instrument is. So I've got a transmitter over here and a receiver over here. Okay, so let's just think about the transmitter. So I got a current that's going in that transmitter. So now the current is going kind of clockwise, and I've got a magnetic field that looks like this. Okay, so just look at the blue. So that's the magnetic field that comes from this transmitter. If I look at what's happening in the ground, okay, I've got the magnetic field comes like this, right? And it's going through this loop, and that means that there's going to be a flux that's going through. There's going to be a current in here that's going to oppose that, and that means that the current is going to go into the board here and out of the board here, so that the magnetic field from that is in this direction. Okay? Current opposes the change. So now let's look at what's happening at the receiver. At the receiver, the primary field is looking up like this, and the secondary field, this is also looking up. So they're in the same direction. And we make the convention that if the primary and the secondary are in the same direction, that we're going to plot as positive. So that gives me, at point A, a positive quantity. Good. Let's now move over a bit. And we're going to be at point, now we're moving over, and now my receiver is sitting up over the cup. So what happens here? Well, from the point of view of the primary field, it's still going down this way through the loop, and that means that there's a current that's induced in here just the same as it was at system A. The current is going into the board at the top, out of the board here, and so the magnetic fields go like this. But look at the orientation of the fields and the receiver. They're parallel. So there's no flux now that's cutting the receiver. That means that the signal is going to be 0. So I've gone from something that's positive, and I know out here it's going to be 0, right? So it's some kind of up positive, and then at some point here, it's going to be 0. The next location, the transmitter and the receiver straddle this. So the receiver is still on the left-hand side, so nothing changes as far as the current in here. But if you look at the primary field, okay, that is coming, so the primary field is Now, in this direction, the secondary field is coming up like this, so they're at opposite sides, and now I get this great big negative. At D, now we have another kind of orientation thing. The transmitter is directly over the target loop. So if I look at the flux from the transmitter, it's going down this way, but now the coupling is such that now I don't get any currents here. So I get another 0, and then at E, I'm over here. So both the primary and the secondary are in the same direction, so I'm plotting phases. There's kind of a lot of stuff that's going on in there, right? I mean, you're like, okay, what's my typical signal? Oh, up, down, up, right. Okay. Maybe it looks like a seismic wave. But but there's a lot of things that are going on in order to really draw this curve out and kind of be able to sketch out, where the currents are, which direction the currents are, where the fields are. That's actually, at an undergraduate level, if you're trying to teach electromagnetics, just to have people being able to really understand how to sketch that curve, then they already know at least something about magnetics. So that's it. That's geometry, right? But remember, if we're in the frequency domain, we've got a real and imaginary part. So now how's that going to come into play? At this point here, I've picked it so that the induction number is actually equal to 1 to unity, and therefore the in phase and the quadrature phase are equal strength, and it's lying on top of each other. So here's what that response curve looks like. Here's the induction number of 1. Gives you this system here where the black is the real and the red is the imaginary, and that's what it looks like. So if you went over this cup with that induction number of 1, then your two curves would completely align. If I change, okay, so let's suppose I'm going to change the induction number. I could do that by increasing the frequency. So instead of having it 10 hertz, I'm going to make it 1,000 hertz. What do you then expect is going to happen to those curves? Dilton? Did I pronounce that correctly?
Sorry?
Your name, is it a Dilton? Sorry, try it again. Adeuton.
Yeah.
Okay. Now we're at a higher induction. And so that could be because the cup is more conductive, or it could be because I'm operating at higher frequency. Either of those wouldn't matter. Okay? So I'm asking what's going to happen to those curves, because there's now going to be in phase and out of phase. Oh, two curves. What are they going to look like? Are they going to have the same shape? A different shape? One going to be bigger and smaller? Nikolai?
Yeah.
Anybody else? John?
So you said the induction number is larger than 1, right?
Yeah.
Then the real part should be larger than the imaginary part according to that response function.
So here's my response function. If I up the real, or if I up the induction number, I'm going to be up here. So now, I go up the scale. First of all, there's the quadrature, but the real is much higher. So what about the shape of the curve? I'm going to increase the frequency, and what's going to happen to the shape of that curve?
So the imaginary part will be squeezed, the real part will be squeezed.
But is it going to change shape?
No, the shape is only to do with geometry.
Right. So this stuff here, the up, down, up, that's just geometry. But now there's a difference in the amplitude. Notice that the quadrature phase is, oops, I went the other way. There we go. Oh, I see it too. Yeah. So we increase the induction number, so we're sort of up here, and there, now the real part is actually larger than the imaginary. Okay? And then if I go the other way to 0.5, now we're back here, so you can see where we are on this response function, and the real is less than the imaginary. And now if I look at the curves, they show that. So the shape of that curve is just controlled by geometry, how everything is coupling. The amplitudes, that relative partitioning, is determined by the parameters, this overall induction number. Okay? And that's why this curve, this response function is so important, because you're always, in geophysics, especially in mining geophysics and in other things too, you're always trying to figure out, okay, is this a good conductor or not so good conductor? It makes a big difference. And so then you're kind of looking for, well, is the information mostly in the real part or is it mostly in the quadrature part? That is a first order diagnostic. And if we look at time, I should have showed you that, but if we did a time domain experiment, so now I'm going to do exactly the same thing. It's just that I'm going to shut this off, and then I'm going to measure the time decay. Okay? But I could make a profile where I look at, at a particular time channel here, let's say 1 millisecond, throughout the whole line, right? Or then I could look at a profile at a different time. So first of all, what do you think the what do you think the data curves would look like? Okay, so I'm going to still do the same thing. So here's my body. Here's my transmitter and receiver. And my waveform now is going to look like this. Okay, so this is t, and I can measure something in the time domain. I can measure a response in the time domain. So my response function, is always going to kind of look like this. So this is my response, and here's time. So if I turn this thing off, then I've got a response function in time, which we showed, kind of decays exponentially. Okay, so now let's transfer that information to the point where we say, okay, I'm going to do a time domain experiment. I'm only going to, let's say I'm going to look at one time, 1 millisecond, and I'm going to kind of go over like this. So what would you expect to have for a response? Anybody?
What they mean? This curve is the response. What they mean by?
So this is what we had in the frequency domain, right?
Okay.
But now we're going to change things. So this was done at a particular frequency, at a particular induction, right? But now we're going to change things. Now we're going to do time domain, right? And then we're going to look to see, okay, what's the shape of that curve? What's that going to look like in the time domain when we do that?
Like a box.
Yeah, for the time domain, it's the experiment is that we've got, first of all, a constant current, and we turn it off. And then, so we know what's going to happen. If I'm sitting here with my system, and Sergio is a conductor. I turn this thing off, I instantly get currents in him, and then they decay away. So that's the system. But now we're actually going to try to take that and transcribe that into something where I've got a transmitter receiver, and I'm just sort of moving like this. And I would like to plot. Over here, you know, some, I don't know, some response at t is equal to 1 millisecond, what the character, what it is I'm going to receive over here. Anybody? Okay, so nothing changes in the physics. So that means all the stuff that we talked about with respect to orientations and coupling, that stays the same. It doesn't matter whether you're in the frequency or the time. So that means that we're going to expect a signal that has got that same character, because that is just coupling. The fact that we're not in time means that, you know, we're just going to have, at a particular time, it's going to, you know, have this particular kind of signal. At a different time, it's going to be exactly the same shape, but it's going to have a different amplitude. So the response function, so we take this shape and then we basically multiply it by whatever the response function was at different times. And so if I did this survey at multiple times, I'd get the same kind of looking thing, but it's just different amplitude. So here was our response function. We could figure out what the amplitude was at any particular time, and then that's reflected there.
So here, basically, for a given time t1, you have measurement at different x locations.
Yeah. Which is that's something that we're going to see a lot of, because what happens in a survey is that you're sitting over here, and you've got a system, and then you measure, you know, the response. This is the response here as a function of time, and it's done in a whole bunch of different time dates. Right? So that's your information. But then you move over here, you fly your system over here, and now you get, you know, another one of these guys. Right? So that's informative. But one of the more interesting things is, like, at the same time, if you know, what does this thing look like? You know, maybe it looks like that as I'm flying over. You say, wait a minute, there's a big response here and a big response there on a horizontal. Okay. So our data at each particular location will have multiple time channels, and but sometimes plotting how everything changes as a function one time. So there is another app. It's the three loop model. This is actually a very nice one to play with. This is a very nice app, and is Jaja. You'll have this is something you make great use of in your course, because these 3-coil responses just capture most of the relevant information that you need for just kind of really understanding what's going on. So here's the idea. We've got an instrument that's a transmitter, okay, and that transmitter is in it's a frequency domain transmitter. So there's a particular frequency that's associated with it. Here's a receiver, and we got a target loop down here. And to specify the target loop, there's kind of an inclination and a declination. And the way in which it's defined here, the inclination is from 90. Just a second. If it's pointing vertical, I think it's 90. No. So the inclination, this is an inclination of 0. So if it's perfect horizontal, so that's the same as in magnetics. Okay. So it's horizontal, 0 inclination, and then the loop can go orient itself down like this. So at 90 degrees, this loop is going to be completely horizontal. So we're working with respect to the plane of the loop. And the declination is from true north. So again, just as in magnetics. So those two, the inclination and the declination, define what the orientation of the target is. And then there's a frequency in here. You can also adjust the parameters of the target by changing R and L. And then you can adjust how frequently you want to sample. So here's all the parameters that you're dealing with. The depth of the target is given by Z sub C here. And here's the inclination, declination, and the response differences. So now if we're going to look to see what the data are going to be like, and check. So for this particular case with frequency of 10,000, okay, we're at a pretty high frequency, and you can see that our response curves, as we're going across, they kind of look something like this. So we're at an induction number of, I guess, about 30 here. So the real part is larger than the imaginary part. And then if we look at our profiles as we go across, you can see that we have that same kind of characteristic. So it goes up, down, and up. And so both the real and the imaginary part have the same responses. And here's what the character of those two things would be. So if you looked at it in plan view at the data, then here's what the data would look like if you went over the whole, if you looked at the data from the whole area, and here's the real part, and there's the imaginary part. And so you can change the, what should we change? We'll just change, let's say, the inclination. So now if we change the loop from being being in this orientation here, and we change the declination and the inclination. Let's just change the inclination. So we can see that you can see how the character of the fields have changed. And also, if you want to change with changing the frequency is the same as changing the induction number. And so if we lower the frequency, if we lower it down to, let's say, 4,700. So notice how this vertical line has shifted back this way. So now the in phase and the quadrature are getting close to the same. And so if we look at what the profile is, then you can see that two things are the same, getting close. And if we bring it all the way down to this lower end here, so here's our, here's the response curve, here's where our, with that particular induction number. And now the real part is less than the imaginary. And so we have something now that looks like this. Okay, so depending upon what the conductivity of the target is or what frequency you are, you might be operating at this level here, where most of the information actually looks like it's in the quadrature. But if you increase that frequency, so you increase the induction, the curves come up to be close to the same. And if you go to really high frequency, then the real part dominates. Yeah.
Geologically, what would this declination, inclination means? What kind of properties in the rocks would influence it? Because of course this is the model.
Right, you can think of a plate. So let's suppose you had so we're going to place the coil by, let's say, a plate, right? So now what's the orientation of that plate? Yep. That would be the closest one.
Okay, and have like a huge volume.
If you have a big blob, then yeah, it's a sphere.
Yes.
So the purpose of this is not that we're actually going to use this in our understand or our computations or analysis. The purpose of this is just to kind of get you connected, right? So now if you've got let's suppose you've got a tabular body, then you could definitely think about that as being, like a plate. And so if it was looking like this or looking like that, then you get a response. So that's as far as we want to take this. But it's a good way of going because you're sort of stepping through in a very simple way all of the things that are happening. Then once you got that, then we'll do exactly what we're going to do in a second, and that is like, okay, now we kind of understand physically what's going on. Let's look at the numerics. And in fact, that's exactly it. So, Ricardo, we've done all this stuff with plates or with little coils and stuff like that, right? So that's allowed us to go a long way. We can kind of sketch out what the curves are like. And we're not going to use that for our analysis, but we are going to use it for understanding. So this next slide here really addresses the kind of question that you're getting to. So like, okay, how good is this circuit model? Mm-hmm. What do we use it for? And you'll see that it's actually not bad. In fact, it's pretty good. If we take an example of a sphere, for instance. So here we're going to put a sphere of 2 Siemens per meter, 30 meters in radius, buried 50 meters deep. We're going to put a transmitter sitting right up on top here. We're going to measure the data over here, so it's 20 meters above that. Everything is basically in free space, 10 to the minus 8 Siemens per meter. Our response curve for that sphere is like this. So that's what we get from the coils. If we actually do the numerical modeling of this, which is done with a code that you will have access to. It's a 2D SIL code that was written by Lindsay and a few other people. You do the numerics, you actually get something that looks like this. So it's pretty good. You get a quadrature part that's got that, sort of a nice sort of peak, and then you get a real part that goes up like this. So that says like, okay, we've got a simple coil model that allows us to kind of get our intuition right. And then we've got some numerics, and yeah, those things actually are not so bad. So I think I kind of believe, at least in general, the ideas that are coming out of COIL. So this, the silk code, there's a couple of papers by Lindsay and also one by Rowan Cockett and others, is a finite volume code, works both in frequency and time, and it uses cylindrical coordinates, so it's kind of like you're able to model a 3D situation, but only if you've got cylindrical symmetry. But it works in this particular case if we think we've got, let's say, a coil that's sitting directly. We've got a transmitter coil that's sitting directly above this, then along this vertical axis here, everything is cylindrically symmetric. So it turns out to be a very useful code. As I said, it's available as an open source resource. So let's just kind of regroup here for a second and see where we are. First of all, we've looked at the basics of EM induction. That's something, so there's response functions, both for frequency and time. We talked about mutual coupling. We've got data for frequency and time domain systems. And yeah, we've shown the circuit model is pretty good. And we've got a couple of apps to do things. So the item that has not yet been accounted for is the following, that we've got to get energy from our transmitter to our target and then have that energy propagated back when this medium is no longer free space. Everything we've done up to now, I said, okay, that's just free space. But what happens if this target that we've got is actually buried in a conductive background? So that is an important point, and that's another step as well. So this is probably a good time just to stretch our legs a bit and get a bit of coffee, and then we'll come back and we'll take a look at that.
Yes, fix those. There's a trick where exploring. Yeah. Somehow, you did actually work. True as a string. True as a string, and then wasn't doing anything. So.
Okay, if you get full on this laptop, so he's just.
Well, this is good. Não, mas eu não preciso ser massa.
Yeah, we had that wrong for ages. I've noticed. I actually had that. Because I feel like we debated about what to call it. And I'm just in the choice to be okay.
So Jake will be here this
Yeah. Like, yeah, okay. Oh, sounds good.
Hey, good, how are you?
Good question. This comment is a little bit confusing. This is supposed to be amplitude.
Yeah.
Amplitude.
Oh, yeah, we're getting negatives. So it should actually.
So that's coming. Have you ever noticed that? Or?
That we.
What's the better way?
It should actually just be HS divided by the L.
I was thinking how I can use to my students when they all the negative values when we divide.
No, just H HS over HP.
Yeah.
There's no,
Okay.
do we have absolute values?
We do put absolute value.
Or you put actually for all the pairs.
We should.
Oh, no, there shouldn't be. That's just
Okay, okay.
HS over HP.
Okay.
Yeah.
Oh, I never even.
Yeah, because when I was looking at this, I was thinking how I can speak to the
No,
Yeah,
no, it's just HS over HP.
Okay, that makes
Yeah.
perfect sense. Okay, thank you.
Well, we actually go to page where people can look at it.
Yeah, that's good.
Which is good.
There's, yeah, a number of places, I think more emphasis should be put on E, DPT, and looking responses versus the other. Tend to kind of slough over that. And since everything goes in E to the minus, yeah, T, kind of. Already like
Yeah, no, that's fair. Well, let's try and get the screen fixed too. Seems to be having problems. Just try something.
So do you have information, is it Ken? So you were tasked with looking at this high resolution.
So I just try to understand how the whole system works. Like, so how many last year is the oil survey for steam injection. So they kind of, so Apple has its own kind of data processing. So they provide a list of parameters. One of the parameters kind of correlate pretty well with the temperature, like resistance. So I try to understand why they get that correlation. It's just an arbitrary.
Do you know what they're doing? Is it all a black box?
I have some information.
yeah.
But
Then if you don't mind,
I
just
try to
share the screen again.
take the results like
whatever.
just the list of parameters we generated. I get like 80% close to the results, but still there's, to me or to us, like the Sherman is still kind of, I probably have some kind of information about how they process the data, but because I'm not a EM background, so I have some difficulty to understand what they're doing better and why they process it the way that they process it. So the biggest challenge currently I have, so they give us the raw data they collect. So yesterday I'm asking you a question about the activity and phase because, so the raw data they give us, how they describe it is like, okay, so they do this kind of stairs. Basically, they just have, let's say, transmitter and receiver, and this is 0.3 meters apart, and then they just fix at a location. So their transmitter will kind of send a pulse, and it's called like wide range, like wide frequency range pulse. So then the receiver will record a sample every 0.2 nanosecond, and then they will record it over time. So let's say, so they have like the first 0.2 nanosecond, 0.4 nanosecond, and they have like a total of 100,000 videos. So they will kind of repeat it, and then they have a total of, let's say, 1,000. We call it a trace. So this is measured over time, every day point to that second, and then they will repeat it. They don't move anything, they just repeat it at the same location, probably send another pulse. So that's my guess, but at least for this report, it's each point, every point to 9 seconds, and they report a total of 100,000 samples or readings. So if you plotted this, the number, they only have one number in each of their cells. So their value in each of their cell is a integer between 0 and 255. So if you plotted this over this way, if you plot it, it will look like this.
So it kind of looks like a radiogram, doesn't it?
Yeah, to me, it's really GPRT. You just use different frequency. So yesterday, I actually, so my first question, I want to understand what it really matters. They didn't really tell us. Actually, they are unwilling to tell us what they actually matter. They just give us the raw data. So basically, there is a decay definitely, and they have this kind of sinusoid kind of like waveform. So basically, based on what you just taught us, like if it's transient or if it's like time domain and frequency domain, neither of them look like this. If it's a time domain, it's just like one curve like that, and if it's frequency domain, it's like usually like that. But what the raw data they provide us is something like this.
Can you actually see like reflections in here? Is there, does it look like a radiogram? The thing about radiograms is they actually look like seismic, right? So anybody who's seismic.
I'm not familiar with seismic actually. So I don't think there's any reflection. So basically, yeah. So as said, I don't know if this is not like electrical field or magnetic field or.
But is it? Do you think this is like just basically a GPR where you've got an antenna? Actually, receiver antenna.
Yes. They have that, so I can go ahead and so
Well, if it is GPR, then the first one here is just that there is actually.
So it's so
Time domain
with multiple pulses.
Yeah.
Because usually that's what they do, and if they talk about broadband, the signal that they put out is kind of a band limited signal. It's got some center frequency, and then there's a pulse that goes out. The width of the pulse is related to the center.
So like something like this is actually what is
similar. So basically, because they refuse to give us their transmitted signal, they only have in one of their paper all of their transmitted signal. So they have frequency of like 1 to 100 megahertz. So it's something like that. So that's the only information we have on their transmitted signal. We don't. It's actually from their from. Yeah, here you go. So that's their transmitted signal.
Yeah.
So they kind of send these calls and then they kind of record whatever narrative in the receiver. And they
Okay,
just-
so because it's such a long time to say
Yeah,
Right.
it's too.
yeah, so then, like, if there is a reflection, it's just gonna be a mishmash. Okay, so that's fine. So it's a radar pulse. So it just happens to have a wave that's more complicated than usual. But on the other hand, there's more spectral at the lower frequencies.
But actually, the temperature variation they observe is at 1,000 feet. I mean, so this. So the dielectric constant, I don't know if you know the dielectric. So we have some injection in this area.
Because that's pretty cool. So you can't get over and so knowing what the electrical conductivity background is very.
Yeah, so to be able to really extend the product to the and so if you're in a really resistant background, then you can see deeper. But if you're in a moderately conductive background, you will be limited. So
Okay.
you have an idea of what the
Okay, I probably can find out. Yeah, this is not my.
Cara, ela vai sair, eu acho que meio-dia. Ela quer chegar cedo de outro
But I
lugar.
can find out tonight. Because that is under steam injection, so we should have water in it, so I won't have
Eu fui dela para Miami, às 6 da tarde, ela vai chegar cedo agora. Ela quer ver se rola uma sobremesa.
Eles chamam de mais área maior,
Yeah, because what I heard, like, it all has like couple hundred feet, so the thousand feet is equal.
So Doug showed the scan.
Tá lá.
That's coming up, so that'll be. It's like a radar signal, but it's a very band,
Como é que isso ajuda a caracterizar de
So it's not like a typical radar signal where you're actually looking at your radar by just seismic. You won't see the flash that you have such a.
Yeah, she was to me, over signal oscillation.
Yeah.
This is not typical for the one.
Oh, yeah. There's usually some, yeah, there's some waveform
assim na
um,
exploração de petróleo, né? Aí tem vários insights aí
usually
que
when you're trying to get some
assim, mas
stuff.
Pelo menos acho que ele apareceu na foto e tava vendo, né? Se eu sem casa, ele não tirou foto. Não, mas ele
Bem mais
Did the index go?
Can you share the screen?
Porque tem uma função que pode ser fácil.
So what did you do?
Oh, there's a couple of bugs in the timing. So every time you look at it, so it was actually running the floor model every time. So
Oh, okay. Okay, great. Okay. So as I said just before coffee, we're pretty much there. There's one kind of major ticket item that we haven't thought about that is extremely important, and that is that we've actually got to get energy from the transmitter to the target and get that energy back. So now the question is, okay, how do EM fields and fluxes behave in a conductive background? Well, that's really the issue. So let's go back to Maxwell's equations. So we can write them in first order that looks like this, but we can combine these equations into a second order equation, which is actually a diffusive wave equation. So this is second derivatives on H, and here's a time that involves, well, this time involves wave propagation, and this is dispersion. For the seismologists in this room, the equations that you generally deal with would be things that don't have a diffusion term in it, but are basically wave propagation. In the work that we do, we actually tend to emphasize this portion, and it's not until we get to actually very high frequencies to do the radar that we enter this wave propagation term. Doesn't really matter. Here's a second order equation. We can work with it in the Fourier domain, so taking the Fourier transform, and we end up with, let's call it a vector Helmholtz equation. Looks like this. So in the frequency domain, it looks like this. And if we make what's called a quasi-static assumption, that basically gets rid of the displacement current. And it's a procedure that holds so long as omega times epsilon, remember epsilon was that electrical permittivity over sigma. If that's significantly less than 1, then we're good to go. We can kind of neglect this term. So here's what we're assuming, and that is going to work in almost all cases for the things that we're doing, just so long as we're at frequencies that are not too high, and not too high means 10,000 or maybe 100,000, and depending on what conductivity we've got. Okay, so let's assume that that's the case. And then this K up here is called a wave number. And if we make this assumption about quasi-static, then we can write K in this manner here as just equal to a real part minus I times an imaginary. We plug that in, and here's kind of the equation that we really want to have. And that says that the magnetic field for a plane wave, let me describe that. So imagine a wave that is kind of like it's got an amplitude that's constant everywhere in a plane, and it's got a constant phase to it. So I think even for the seismologist that would be, you tend to think about plane waves as you're thinking about waves incident on a reflector and then bouncing back in. So these are plane waves. So we have the same things in electromagnetics. And if you wanted to kind of physically conjure up, like, okay, how on earth could we get a plane wave? You might think about just imagining a big sheet of current someplace up in the ionosphere. And a sheet of current gives rise to a uniform magnetic field underneath that goes, the current is going in, let's say, in this X direction. Then the magnetic field, again, kind of by the right-hand rule, is going to be in that perpendicular direction. So we have an electric field in one direction, and 90 degrees perpendicular to that, we've got a magnetic field that is into the plane in this case. Okay, so so now imagine this magnetic field, the plane wave is just kind of propagating down. So how does it propagate down? Well, first of all, it propagates with a phase, so it's a wave, it's propagating, and here's the phase, but it also attenuates. This is an important aspect for us because this wave, as it propagates into the ground, is attenuating according to this exponential. So the alpha here was part of this wave number, and it's given by the square root of omega mu times sigma. So permeability is in here, conductivity, and frequency. The wave attenuates as it goes into the earth, so it has this exponential decay, and there's a particular depth at which this wave has decayed to about 1 upon e of its value. So if it starts at the surface at 1 and it decays exponentially, then at some point here it's decayed at 1 upon e, and the depth of that is called the skin depth. There's a formula, so the skin depth is given by this formula 503 square root 1 upon sigma f. So here's a few things to kind of keep in mind. The skin depth, which is basically telling you how far into the medium something can travel, is inversely proportional to the frequency and the conductivity. So the higher the conductivity, the faster the waves attenuate. The higher the frequency, the faster the waves attenuate. So let's look at what happens now in a homogeneous medium. So let's suppose that I take a plane wave and I simply shut it off, or I put an impulse in at time t is equal to 0. So imagine that I've got a magnetic field, it's a plane wave, but it's just sort of instantly on and off, so it's like a delta function. And then how does that information propagate into the earth? So you can imagine in seismic, for instance, if you do that, okay, if you have a pulse and it propagates in, then it just propagates in. When it hits Sergio, it's still a pulse. When it hits Ricardo, it's still a pulse, and it just goes, right? That's not true in electromagnetics. What happens is that pulse kind of goes in. So this is time, and this is amplitude, and as as a function of time, if we looked at what is happening, here is the amplitude as we go in. Or if you wanted to take a snapshot at a particular time, so let's suppose we've set the pulse off, there's a little bit of time, and then I just take a snapshot. What does it look like? Then we find that the pulse actually looks like this. So this is now depth as a function of amplitude is a function of depth, and it kind of looks like this. So this wave, as it's propagating in, is losing amplitude, it's broadening out, it's diffusing into the into that background. One of the things that's of interest in here is sort of like, okay, where's the peak at least of this wave? If I look at a particular time, where in depth is the peak? And at this particular time here, the peak is at about 70 meters. A little bit later, this peak would have moved over and would be at 80 meters, 90 meters. So we call this the diffusion distance. So we need to have some way of kind of having an idea like, okay, how deep has this wave penetrated at a particular time? So we call that the diffusion distance. But as you can see, it's not really crisp, not like in seismic. In seismic, if I looked at this plot here, it would still be a perfect, seismic pulse, and it would be at a depth of 70 meters at a particular time. A little bit later, that pulse would have traveled on. Here, now we've just got something that goes in, kind of swooshes in. So we're going to talk about diffusion depths. We're going to talk about skin depths. But these things are just kind of representative of, sort of how things are going. So don't get too detailed about the exact decimal points. We have an app that you can experiment with. It allows you to institute a plane wave. So I told you kind of how to think about generating a plane wave, and then you can change the frequency. You could change the physical parameters, conductivity, permeability of the Earth, and just sort of see what the wave looks like as a function of depth or as a function of time. That's kind of nice. You can play around with it and just kind of get some sense about what's going on. Okay, now I want to look at effectively a dipole source. So now imagine that we've got a current loop, okay? And we're going to either put a frequency or time domain signal through that. And we're going to actually, most of the time, we're going to look at what's called a vertical magnetic dipole. So there'll be a loop source, and that's probably going to be parallel to the Earth's surface, and we're going to fly that around. But occasionally, we'll want to change the orientation, and we're going to have a horizontal magnetic dipole. So these are the two things that are. So let's walk through this and see what we got. So here's our representation of the Earth. So it's a cube. There's X and Y. And there's two planes on which you can visualize things. So there's sort of a horizontal plane, and then there's a cross section. The base model that we're going to have is one in which there is a horizontal loop. So horizontal loop means vertical magnetic dipole. That's going to be 20 meters above the surface. The background is going to be 100 ohm meters. And we're going to do a time domain system where we have a step-off waveform and look to see what the responses are like. So let's just think about this for a second. So we've got a loop of current, okay? And so we've got a constant current on it, and we're going to shut it off. There's an earth under here that's a conductor, so it's not a little coil or target. It's just a homogeneous earth. So what do you think is going to happen? Let's think about currents, because that's the way that we, first of all, try to think. So imagine I've got a current in a loop, and then I shut it off in the presence of the conductor. What would you expect might happen? Anybody have any intuition?
will generate a primary magnetic field. So it will generate a primary magnetic field that will interact with the subsurface conductive media, and it will generate secondary magnetic field. Due to this primary field will generate currents, edge currents.
Okay.
It will generate the secondary magnetic field. When you switch off this primary magnetic field, the secondary will disappear, but with it's proportional to the conductivity of the medium. If the medium is high conductivity medium, this magnetic secondary magnetic field will disappear more less rapidly.
Right. There are a lot of things I like about that, but I'm just not 100% sure. So let's suppose here's our transmitter. We've got a current in here, and let's first of all, we're going to do two things. We're going to shut it off. So let's first look at this point here, which is kind of the on time. And I could draw two sections. One which is kind of like a cross section. The other is I could draw a plan view, and let's suppose that this point here is directly underneath here. Okay, so now we're in this situation here. So now I've got currents that are going like this, so that I've got magnetic fields that are going like this, right? In this situation, you mentioned about the currents in the Earth. So what are the currents in the Earth then at this situation? Zero, right? So at this point here, when we're sitting up in steady state, there are no currents in here.
If you think of Faradays Law, depends on the variation of the flux, right?
Right. Okay, so at this point, there's no currents. Now let's change this so that we just turn it off. I'm going to draw it. Here's point A, B. Now I'm going to change this. So up here, there's no current anymore, right? So these guys are gone. What's happening in the Earth?
A transient, if B is far apart, to be the same as A. It's nothing at all. But in this transient point, to induce a current in the Earth. Okay, good. And what do you think then? What do you think those currents would look like?
In such a way to avoid the change of the magnetic field.
Right?
And if you think in Lenz's law,
yeah,
circular to create a flux that will create a field that goes up. So current in this direction too. Perfect. So immediately we turn it off, then we're going to get currents that are set up in here. They're going to go in on one side, come out on the other. They're going to be circular currents, and those currents are going to be such as just to oppose in any change. That's it. If we take this, so this is exactly it. This is exactly what happened. I'm going to do this one step farther, and if I put the current right, let's put the current loop right on the ground. Okay. If I put it right on the ground, I turn it off, and then I look to see what are the currents
in the ground immediately after shutoff, then what do you think those currents would look like? So it's kind of like an and member. The current loop is right on the ground, and I turn it off, and just immediately after I turn it off, there's no current now in that wire. So there must be current in the earth, and what is that current going to look like?
The same as the wire, but in the opposite direction.
Same as the wire in the opposite direction?
It could be, it must be the same direction, right? To recover the same field direction that it was in the Earth before. And then it will, anyways.
Rest of the group, agree, Sergio, Virgo. Current goes opposite to somehow opposed, it goes in the same direction. Okay, raise your hands. How many agree with Sergio? Wow, it's like, oh, I have a lot of friends. I've been in that situation. How many agree with Roberto? Yeah, he's got more. And how many people are just like be happy enough to go to tequila bar? It's a little early. Okay, so Roberto is right, and the way it has to be right,
Same.
because you have to produce exactly the same magnetic field. So the current has to go in that same direction. So this is actually, if you think about it, kind of an amazing thing, right? Because you've got a wire. It's a loop, but it could even be straight wire. And the current is actually flowing in that wire, right? And then you've got your hand on a generator and you turn that off. And immediately after you do that, the current's not in the wire, it's just right underneath. Isn't exactly coincident with that, right? You've just transferred the current from the wire to the ground, which is all kind of amazing, right? And now once you've got the current in the ground, then it's just going to dissipate. So that's what's going to happen. So now we look to see what happens. So the currents, so at some time after you shut off, the currents have already kind of gone into the ground, but you see that they're circular currents, so they're following the same geometry as as that primary field. And at some point, then they look like this. So here we've got currents. They're positive on one side, negative on the other, and that's their distribution. What's interesting here is that we could actually look at the propagation through time of this. So at early time, after we've shut it off, here's the currents. They're sort of in and out, positive, negative. At a little bit later time, at 0.01 milliseconds, it's like that. Later time, it's like that. So you can see what the currents are doing. You initially have this kind of image current, and then after that, it just propagates away.
Yeah. So just an observation, it spreads. Of course, if you look at the numbers in the color scale,
yeah,
you're changing the color scale. Okay,
yes,
it's spread, but the amplitude is going down very fast.
Thank you. I didn't mention that, but yeah. So these color scales here, the amplitude is 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. So it's really getting small. It's dispersed. Yeah. There was a very famous paper written in 1979 by a guy Risak Nabigian, who mathematically showed that representation of this could be basically a set of smoke rings that would reproduce that field, and those those smoke rings kind of diffuse downward and outward. So here's some important points. The currents will flow in the same plane as the transmitter currents. They diffuse downward and outward. Each transmitter has a footprint, and so that footprint is determined by where the currents are. And the maximum resolution will occur at the earliest time. So this is intuitive. At the earliest time, the currents are the most concentrated near the surface, so you're getting sort of finer scale resolution. And the maximum depth of penetration will be at the latest time that everything is. So that the earliest time and the latest time, where the currents are, kind of tell you where you're seeing and what your resolution is. One of the things that you should see from this, okay, is let's look at this guy here. These currents are really spread out. So you're looking at some late time. You're at 50 meters depth. You're not going to see resolution of a meter, okay? So these kinds of images, I think, help kind of set the expectation for what you're going to see. At any particular time, you're going to measure something that's going to come from all of these currents. So it's nothing localized at all. So now let's look at the effects of the background. We've already kind of decided that it's going to do something. So we saw that if we have a transmitter, their energy is going to get attenuated down to the target, and then we're going to get the currents in here, and then it's going to propagate up, and the energy is going to get attenuated up there. Okay. So in this first example, okay, we've got a background of 10 to the minus 8 Siemens per meter, and we're at a fairly early time, 10 to the minus 5 seconds. And if we look at the currents on this sphere, so the sphere is 2 Siemens per meter. So this is kind of interesting, right? We've got currents that are on the outside of this sphere. Maybe an appropriate question at this point is why? So here we're at 10 minus 5 seconds. You know, if you kind of think about the transmitter being up here, and thinking about illumination, why is it that you just don't like have the top half of the sphere? Because it's sort of high, and then it kind of, you're not really seeing the inside.
Like the surface charge circulating.
Surface what?
Surface charge, the electrical charge are just in the surface, and they are circulating.
Wow. Yeah. Okay. So first of all, we don't have any currents crossing a boundary, so we're not going to get any charges like we did in DC resistivity. Okay. So there's really no.
Yeah, it's no free charge.
No free charges.
Yeah, of course, but you do have this inducing currents in this.
Correct. Yeah.
The surface inducing currents.
So, but why are they just in the surface? Why aren't they?
It's the kind of polarization, membrane polarization.
No. Did so well with the tequila.
Priorities.
You can answer all the questions about tequila. Any other? Luis? Okay, remember we were talking about electromagnetic waves in the time domain propagating, yeah. And what was the thing that was really important on that with respect to how deeply something could penetrate, or kind of keeping track of where the penetration of that wave was? What was the term that we used?
Frequency, conductivity.
Yeah, what was the term that we used? No, in frequency domain we talked about skin depth. In time domain we talked about diffusion distance. Yes. Okay. So remember the diffusion distance. The diffusion distance D, I don't know, something like 1300, 1 over
T over conductivity, T over
T. Yeah, I think that's right. Should remember that. Anyway, the point is, the larger the conductivity that we've got, or the smaller the time, the smaller diffusion distance. So here we're at 10 to the minus 5 seconds. And sigma of this is 2 Siemens per meter. So if you do all of those numbers, you find that you only have something in the order of a couple of meters. So even though at this particular time, at this particular time, 10 to the minus 5 seconds, even though there's energy that's coming in, you can see it's trying to come in, it hasn't diffused in that much. So everything is kind of around the outer side. So this is often referred to as a kind of an inductive limit type of problem. All the currents are just on the outside skin. We don't see them underneath here because there's no illumination. There's no way of getting stuff in. But initially, all the currents are up there. If we actually step through time, which we'll do a little bit later, exactly, the currents are kind of going to diffuse in, and then we're going to be in the inside. But right now, we're in that kind of inductive limit, and the currents are just on the outside. Okay, and we're going to stick with that. Now what I want to do is to change the background of conductivity. Okay, so let us, where before it was 10 to the minus 8, I'm now going to make it 10 to the minus 2 Siemens. We're going to change it by 6 orders of magnitude. So what do you think is going to happen? I'm going to increase. What should happen? What should happen if I immerse things in a conductive background? Yeah. So we talked about propagation through, right? So I increase this background. I'm probably going to expect like, oh, I'm going to lose a lot of energy. So if I lose energy, I'm not going to illuminate this, right? Okay, so let's change it. 6 orders of magnitude. What happened? Just before here. 6 orders of magnitude is a lot. This is now 10 to the minus 2 Siemens per meter.
Yeah, but it's still this. If you compare with the 2, it's still very small, right?
The issue is really what the diffusion depth is in the background. So it's getting the energy here. And at 10 to the minus 5 seconds, and even at 10 to the minus 2, this diffusion distance is still large compared to that. So I haven't lost a lot of energy before I reach there. However, if I now make it 10 to the minus 1, now you're starting to see what you think could happen. So look what's happened now is that we've got currents in that upper region, in the half space. There's still some that's sneaking through, and we're seeing this here. Okay? But we've got a lot of currents that are induced in that conductive half space. And now if I increase it even more to 1 Siemens per meter, that's it. My currents are all Well, I can't even penetrate the background. So this is, I think, very illustrative of some of the really fundamental things that are going on. You're trying to see something down here. The background can obscure things. The background is a conductor, right? So maybe that's all you see. So this is the effects of the background resistivity in time. Change the background, not so much. Here you're really starting to affect it. Yeah, so now what we want to do is to look at the same thing in frequency. One of the, and maybe people haven't had very many courses in electromagnetics, but generally, when you take a course in electromagnetics, information about frequency is provided first. So you do the frequency domain first and then the time domain. And the reason that you do the frequency domain is that in principle, it's easier to solve because now you're just working at one particular frequency and the equations are easier. However, the frequency domain is more challenging to really interpret because you've always got this partitioning of currents. So there's currents there, that's okay. But then how much is in the real part, how much is in the imaginary part? That actually makes things complicated from the point of view of kind of physically understanding. But the physics is the same. And what we've come to realize, and we didn't start out this way, but in the presentation of this course, we've come to realize that the easiest way, the most insightful way to present this is in the time domain first. That's why I showed you the time domain. And now we want to go to the frequency domain. Physics is the same. So you should kind of expect the same kind of phenomena as we have time domain. And here's what we see. So in the frequency domain, and now we're working at a frequency of 10 to the 4 hertz, okay? So it's high frequency. Here's what we see for the currents. Right? Looks pretty much the same. If we change it to 10 to the minus 2, see that. If we change it to 10 to the minus 1, see that. 1, we see that. So this is it. These are the currents from a high frequency. So notice, so we do a time domain. We do a time domain experiment, and we look at sometime t is equal to 10 to the minus 4 seconds. And we look at a frequency domain experiment at 10 to the 4 hertz. And we get more or less the same answers. And so in general, they're not going to be exactly the same. But as a first shot through, if you're working in the time domain and you're looking at the currents, okay, and you see what's illuminated, what's not, if you thought about doing a frequency domain experiment at the reciprocal of that time and translate that to frequency, to hertz, you're going to get pretty much about the same thing. So that's really kind of interesting, and also it helps a lot with trying to anticipate, what it is you're going to see and how your intuition is. So what have we learned at this point? Well, we did the stuff this morning with respect to looking at the circuits, need to account for the energy. So I think now we're ready to look at a couple of field examples. So we got a lot of case histories, and I'm not sure we're going to get through absolutely all of them, but we're going to do almost all. We've already seen 2. So in DC resistivity, we did the Mount Isa, that was the mineral exploration. We're going to come back to that. And then we did the Athabasca oil sands, the monitoring. And now going to look at time domain systems. We're going to apply it to water problem in Denmark, There's a mineral exploration, and then there's a use of time domain EM for near surface structure for getting better velocity models and static corrections for area in Saudi Arabia. So those are three that we'll do for the time domain. Yes. So actually, so that's time domain. So then for frequency domain, I guess we're showing off. For frequency domain, there's another water problem. There's a crosswell. This one you will resonate with. It's kind of your problem here, water flooding monitoring. And then there's minerals example. This one's kind of nice because it compares both frequency and time domain. And that's insightful. Then we're later, so we're going to do all that today. Then tomorrow, we're actually going to do grounded sources. So here's where the marine CSEM comes in. There's an example for India, the Deccan traps, that was basically hydrocarbon motivated. There's Barents Sea, hydrocarbon de-risking, and there's gas hydrates for marine CSEM. Do you know if there's any interest, enthusiasm for gas hydrates from Brazil?
We have occurrences of extreme north and south of Brazil, but no commercial interest yet.
We performed a CSM acquisition in Pelotas Basin, southmost basin offshore Brazil. We have a huge hydrate accumulation, but it was for geohazard.
Okay. Yeah.
Not for commercial purposes.
Yeah.
We're not exploring.
Yeah. But actually, yeah, for geohazard or for exploration, both are interesting. So it would be an example for CSEM for hydrocarbons. And then we'll go to natural sources, and we've got an example for magnetotellurics in marine. For geothermal energy, and then you can also do kind of natural sources in the air, which is kind of interesting, and we'll show you an example of that, as well as combination for MT and ground work. And then there's a Red Sea. This will be magnetotellurics and CSEM for trying to delineate complex geology when you've got salts and various types of structure that is really screwing up your seismic analysis. Yeah, so the airborne work, it's called a ZTAM, so using natural sources but measuring things in the air. We've got two examples for that. Then for ground penetrating radar, there's actually an interesting one for self-driving cars in use of GPR. An IP for landfills. Actually, this is something, perhaps not Petrobras particularly, but certainly in Brazil, potential use of induced polarization for finding old waste dumps and things like that. This is a problem that seems to be cropping up worldwide, and I'd be surprised if Brazil doesn't have cases where it's of interest. And then we'll go back to the example that we did with Mount Isa for the IP. One thing that is an advance for really trying to make use of IP is EM decoupling. We'll talk a bit about that. And we want to kind of close up with an example that we've been doing at UBC that looks for multi types of data use of airborne EM and IP to find kimberlite deposits. So that's it. That's kind of a suite of case histories that we'll be able to progressively look at as we go through the next few days. So now we're going to go to inductive sources. Oh. Yeah. Oh, maybe my Sophos is screwing me up again. Oh, now we got lots of them going. Well, while my computer is.
Oh, it is.
So now I have basically pretty much all the theory that we're going to be released this time. And now what we're going to do is kind of switch to, okay, let's do a serious survey here and look to see what the instrumentation kind of looks like, what people would measure, and what you'd expect for a response. Thanks, Lindsay. Okay. So there was our motivation. It's the same that we had before. We're going to do this in two steps. We're going to talk first of all about the transmitters and receivers. So that'll be both frequency and time. And then we'll go to the time domain and we'll look at vertical magnetic dipole, look at the propagation, and then we'll do a few case histories. And we'll also look at horizontal magnetic. And then after that, this afternoon, we'll do the frequency. So here we are. So here's some important questions that we just have to go through. So first of all, okay, what's the target? Is it a surface? Is it depth? Is it 1D, 2D, 3D, whatever? Then our transmitter, what's its location? Where is it? On the surface, in the air? The waveform, is it frequency or time? What's the size and the orientation? It's like, because if we make a loop that's bigger, okay, then we're having a bigger dipole moment, we might be able to see bigger or deeper. What's its orientation? Exciting the target, you're trying to find something. What's the conductivity of the target and the host, right? Because you're both of them. And then you have to worry about geometry, coupling. And the receiver and the data. So which fields do you want to measure? E field, H field, what instrument do you want? So these are, these are a lot of questions, right? And then where to collect the data, how accurate, what's the depth of investigation, can actually see something at depth, and what's the footprint of the system. So I think as we go through this course, you'll come to realize that it's just not a particular easy answer. And in some ways, I'm not sure how much overlap there would be with seismic. I mean, in seismic, you can have different kinds of sources. You can have explosive source, you can have fiber-sized source, or something. But in electromagnetics, they can be quite different, right? I mean, the difference between a grounded source and a conductive source is hugely different. So there's a more basically survey design. So we're going to kind of revisit that. So here's the basic experiment, which we've seen before. And now let's first of all think about transmitters. What do we got? Well, we got large areas. We might have rugged terrain. So we're probably going to want to fly those guys. And we could fly a frequency domain system. So this is kind of what we'd shown schematically in the cartoon. So in that frequency domain system, there's both a transmitter and a receiver. Or we can fly a time domain system, and most of those involve a larger loop. And that loop could be slung below the aircraft or helicopter, or it could actually be tied onto the helicopter. If we have deeper targets, then we need to have a bigger source. Okay? To make a bigger source in electromagnetics, we need a bigger moment. And remember, the moment was the product of the current and the area. So sometimes we have like a big loop, a couple of kilometers on the side. That's not uncommon. And we just lay them up logistically, so that's a fair bit. But you've got a kilometer, a couple of kilometers around, and that is big enough to kind of see the target's depth. The transmitter, as I said, could be time or frequency. The key factor here is the moment. So the moment is the current times the area, but sometimes you can actually have an extra loop of wire going around. So you've got 2 loops of wire or multiple loops of wire to increase the moment. And then the magnetic field, as we said, falls off as 1 upon r cubed and depends upon the dipole moment. So those are the main things. And if you're wanting to excite the target, so remember, that's always our first thought. Like, okay, we've got to make sure we excite this thing that we're looking for. Then we want to be as close as possible as we can to the target. So we got closest we could generally get is ground-based systems, but we could also do a helicopter, it's a bit more, and higher up we could use maybe a fixed-wing aircraft. So there's trade-offs in this, and we're always concerned about coupling. Receivers, we just talked about B and DBDT. And the in the time domain, the receivers, so if we look at the receivers, they could be mounted in various places. So here's the case in which the receiver is actually sitting right here. It's sitting right at it's on the transmitter loop. So this is the transmitter loop, and there's the receiver. And it measures 3 components. The other thing is that you can take a receiver, you can tow this receiver. This is actually a total field magnetometer, so it's like a cesium vapor. This is an interesting example where the transmitter, the loop of wire, is actually sitting right at the surface. So it's just put down there. And then they do a time domain experiment, but they actually measure the data in the air. So these are the flight lines that are going through. So it's carrying this total field magnetometer, and it's going back and forth. Meanwhile, this transmitter is continually pumping out the current, this time domain current waveform. So all kinds of configurations are possible, and many of them have been tried. And depending upon what you're looking for, one configuration might be a little bit better for you than another. And the only way to make some assessment of that is to do numerical modeling and find out what you've got for signal. In the frequency domain now, Kent, we're coming down to your component question here. So this was that resolve system, and it's got 5 sets of coplanar coils. So horizontal coplanate coils. And each coil system operates at its own frequency. It also has one set of vertical coils. So those are called coaxial or horizontal coplanate coil. And that's given by here. So the frequencies in this particular case are 400 hertz, 82, 140 kilohertz. So they expand a range of couple orders of magnitude. So that's important too, right? Because high frequencies are going to sample the upper surface because it's skin depth. Lower frequencies are going to sample. Here's that EM31 that I kind of talked about when we were sort of doing the example of the cup. The transmitter receiver operates at a single frequency of 10,000 hertz. That's about 3 meters length, and you just kind of walk over. Very simple system, but one that is effective. We need to worry about this primary field. That is the big problem with frequency domain systems. The darn primary field is always on. So you have two ways of working with it. First of all, you might be able to compute and subtract what it is. If it's in a fixed system like this, and you know exactly where the transmitter is, you know where the receiver is, you can compute what that primary field is, subtract it out. Possibility A. Possibility B, and this is one that's often used, is that you have a bucking coil. So here's a little coil that's sitting right by the receiver loop. It's pretty close, but you just need to adjust the current in this bucking coil so that the flux, the total flux going through here, is exactly the same as the flux from the primary. And then it's in the opposite direction, so those two things just cancel out, which means that the flux that you're measuring is then just due to the secondary field. Okay, so that's the other way. But the big issue with these frequency domain systems, primary field is always off. Okay, so where to collect data, how many, all those things. These are really questions of survey design. And there's a lot of parameters. And I think the first thing to do is just kind of let's walk through something that's representative and a bit straightforward and simple, and just see what we're up against as far as the fundamentals. So here we are. We've got a transmitter. It's on. Then we turn it off. It stays at 0. If we're measuring the magnetic field, okay, at a receiver, that magnetic field would just go down like this. If we're measuring dB/dt, then because we instantly turn this off, there's like a delta function, and then there's a decay. This decay of the fields are the secondary fields that are obtained from the target bodies. Okay, so that's kind of what we're expecting. Let's just take a look at what the fields are both before shutoff, t is less than 0. We'll use the time t is equal to 0 to be, that's the shutoff. So we're going to shut it off at t is equal to 0. And then look to see what happens later on when we're just measuring the secondary. It's very instructive to look at the currents, because that's really what's exciting. So we're going to continually look at what the currents are like at any particular time for a configuration. So we'll look first of all at a homogeneous Earth. The setup is that we've got 20 meters above vertical magnetic dipole over half space of 20 ohm. And so we have two planes we can plot in a cross section, and we can plot in 5 meters. So depending on which fields we're looking at or currents, we'll plot one. So first of all, let's look at the currents. Okay, we want to kind of walk through this morning. I've got a source current that's circular. So I turn that off. That's going to give me circular currents in the Earth. So it's sort of, there's the plan view, they're circular. And if I look at a cross section, they're going to be going in to one side and then coming out the other. So what do you think the magnetic fields would look like from that? So I've got, so that's a cross section. So now I've got like this whole distribution of kind of current filaments, current loops that are going through. And I mean, ultimately, I'm going to measure the magnetic field. So what do we think the magnetic field from this guy, this distribution of currents would look like? And this little red dot up here, that's where we're going to measure the fields. So what do you think? So those are the currents. What do you think the magnetic fields would look like in this volume? And ultimately, we're just going to pick. We'd like to kind of visualize what the magnetic fields look like, and then also, in particular, we're interested in that particular slide.
Está entrando.
Então, você está fazendo assim, ó. A gente faz isso para ver se ele está subindo.
Upwards.
Upward.
Yeah. So each circular line filament kind of gives me that dipole field, so that the main magnetic fields are going to be kind of at that central point of the current density, and that's where they are. So the biggest magnetic field is here. We're up here someplace, and we're going to measure what that might be. Now let's look at propagation through time. So remember, here was that formula we had for the diffusion distance. So 1300 T, so that's time, resistivity, and we're at 100 ohm meters resistivity. So we turn this thing off and we look at 2 microseconds after, and the diffusion distance from here is 18 meters. So we look at the currents, and you can see, like, okay, here's the bulk of the currents up here. So 18 meters is kind of in about there. So it's sensible. But again, that 18 meters, you've just got to remember that doesn't tell you exactly like where the currents are, right? The currents are always diffuse, and this is kind of telling you kind of about how far things are diffused. Later, at 0.01 milliseconds, see how the currents have gone down there? There's the magnetic field. Later, at 75 meters, diffusion distance up here. And at 0.1 millisecond, things are out here. So we have this situation here where, again, the currents are flowing downwards and upwards. So that's the important points. We've seen the slide before. Each transmitter's footprint, earliest times give us the highest resolution, latest time give us the depth of investigation. Okay, so that's fine, that's a half space. Now let's do something a little more interesting. Let's put a layer in there. So we're not going to take the same geometry, but we're going to have a layer in here that's 20 meters thick, and we're going to change its resistivity. Okay? So let us make it, first of all, resistive, and then we'll make it progressively more conductive. And what I want you to think about is to try to anticipate, okay, what's going to happen? What the field's going to look like? What are the currents going to? So first of all, if we just have that layer as that background half space, we get what we had before. Now we get a current that looks like that. Okay, so what happens if we put a resistive layer in there?
Distance would be higher.
Okay, that's good. What about currents, both in the first 20 meters above the resistive layer and the currents in the resistive layer? How do they compare? Anybody? Pardon me?
The first layer will be more conductive, right?
Yeah, so the first layer still stays 100 ohm meters, but the second layer is now resistive. Okay, so let's, what would we expect to see for currents in the second?
Yeah, be less dense. Second layer.
Yeah.
Compared to the first,
And why?
because it's more resistive.
If you think of Ohm's law, a higher resistivity.
Yep.
Would imply a smaller current, right?
Yeah, good. So that's what I see. So at this level in here, I mean, there's still an electric field, but J is equal to sigma E. Sigma is really small, so there's not very much. What's going to happen if I make it conductive?
Will be stronger.
If I make it conductive, now the currents are just concentrated in there. Right? So that's what we're really seeing. And if I make it more conductive, what's going to happen? Concentrated, yeah. So it doesn't even get through.
And the depth.
The skin depth, right?
Yeah, that's fine.
It is like, doesn't get through. Okay, so this is like how a background conductivity can affect things. There's something else to be gleaned from here. If you're going to do a time domain survey over an area that is even 1D, what you're going to see is the conductors. So if there's a conductor in there, you're really well coupled with that. If you're a resistor, you don't see it. So EM induction sees conductors, it doesn't see resistors. And here's what the magnetic fields look like. They're kind of interesting pictures. They're actually moderately complicated. In the, here's the half space, here's what happens for the resistive case, here's the conductive, and here's the very conductive. And remember, we're just measuring something that's not taking place. The data that are acquired in a time domain survey are often called a sounding. And what you mean by a sounding is that it's the response, in this case it's dB dt, against time. So for 100 ohm meters, that response is basically just this decay, t to the minus 5 halves, that is characteristically uniform. Or if you have a resistive layer in there, then the half space is the solid line, with the layer is the dashed line. So you can see like there's really not very much difference. That's really pretty small. However, if you put the conductor in, there's a lot. Right? So here's the layered earth. So notice how the curve kind of comes up, it goes down, and that's close to an order of magnitude difference in the signal with that conductive layer in here. And with a very conductive layer, you get something that looks like that. So EM induction, very sensitive to conductive layers. And there's an app, there's a vertical magnetic dipole. Maybe we'll look at that right after coffee, just to kind of refresh memories. So we only have 15 minutes here at lunch. So there's a vertical magnetic dipole app, and kind of walk you through those. This is the app that actually produced those images that we just saw. So let's now look at a conductive sphere. So now we're going to have a sphere that's buried here, and we're going to do a survey. So we don't know where the sphere is. So we're just going to do this survey at each of these dots over here. So this is the easting and northing directions. At each dot, we're going to do a sounding. And then we're going to take that information and plot it out. And we're going to look at profiles that go right through here. So these are going to be plan views. So these plan views are all at one particular time. And a profile is what the values are along a line at one particular time. Okay? So at very early times after shutoff, everything is basically uniform. The waves have not even got down to this conductor. And you got a map here that is just basically a constant. If I go to a little bit later, 45 microseconds, if I look at the map, you can start to see, oh, there's something that's coming out here. And the profile is showing a little bit of a bump. So this is dBdt. These numbers here are the logs. So one of the things you have to keep in mind with respect to EM data is things change a lot. So the data plots are usually logarithmic in amplitude. So whereas we first started off with something that's 10 to the minus amplitude 10 to the minus 5, if we go to this next time channel, we're at 10 to the minus 6. Okay? But nevertheless, if you do this profile, you see there's a little bit of a bump here. You look at plan, you can get that. A little bit later, you're kind of hitting a bit of a sweet spot here. So this is 0.3 microseconds. The sphere is really shining up here. And the plan or the profile is looking like this. So a very, very nice bump right over top of that sphere. A little bit later, things are starting to die out because the waves diffuse. Sorry, Marcus. The waves diffuse into the sphere, and then they'll gradually dissipate out. At the end, everything is gone. So now we're back to something that is lower amplitude, and eventually here we're at very, very low amplitude. Right? So at each location here, we do this sounding. We can plot those data up at particular time channels over the whole area or cross sections or whatever. And in this case here, when we got that conductor, we actually get a pretty nice image. So our summary and for the airborne data is that at these various maps of various time channels, we get something that looks like that. And there is a particular time at which we have like the greatest sensitivity. We pick that body up at 0.3 seconds. If we did a sounding out here, here's with the background and the dashed lines, and the solid line is with the I'll just make a mention that sometimes you see plots like this. When you first look at them, they can be a little bit confusing as to what's going on. But what we're looking at here are these are profiles, but at individual time channels. So this 10 to the minus 5, that was like that first time channel. There's a later time channel. Here's the later time channel. And here's the last time channel. So it's a way of kind of consolidating the data and looking at how things are changing as a function of time. And when you look at this, then you're often looking for little bumps, okay, in here. So high values at some particular set of time channels, and then say, here's. So what are the airborne systems like out there? Well, they take a whole bunch of configurations. So there's one that has a transmitter that looks like this. This is called a SkyTem system. So it's got an area of 300 square meters. So it's pretty good size. And it has a waveform. Actually, it's set up so that it's got a dual moment. There's actually two sets of coils that are going in here. They're kind of in this plastic sheet. And there's one that's called a high moment. So the waveform goes up like this. So rather than this square wave that we talked about, it turns out if you're talking about a current, you can't just jam it on and then you can't just jam it off. It doesn't quite work like that. So you tend to turn it on, in this case, kind of exponentially, and then you turn it off, but it's on a very short ramp. So it kind of ramps on. And then you start measuring in the off times at a whole bunch of time channels. So let's go from 47 to 8800 microseconds. The low moment, so this has got 90 amperes, but it's got 4 turns in that. Remember trying to get moments of current, area, and number of turns? This has got 4. So that's got a big moment. This low moment has got a peak amplitude of 40 amps and only a single turn. So that means you can turn it off more quickly and get earlier times. Getting the earliest time is extremely important because your best resolution of what's going on the surface is in those early times. So that's, you want to turn this thing off as fast as possible. And the last decade has seen, instrumentation manufacturers trying to get these turn-off times down and still get consistent power in. Get those down to a microsecond, something in that order. The VTEM system, we'll also see examples of that. It's a little bit of a different configuration. So the transmitter is sitting out here, and the receiver is in here. And it's a little bit more like the 2-coil system with the transmitter up here, receiver in. And their waveform is a little bit different. It kind of comes up like this, and it's got a smaller ramp off, and then. So every system that you deal with will always have, they'll have their own kind of waveform that has been tailored for their purposes. It'll go up, and then it'll go down. You need to know the characteristics of those waveforms really accurately. So that's one thing. If anybody supplies you with time domain wave data, then you say, well, what's the waveform, right? And make sure that they tell you. The other thing is, there's sometimes a question about when t is equal to 0. Like when are things shut off? When do you start counting? Some people count from the top of the ramp, some people from the bottom, and if you're ever processing these data, that drives you crazy because you just don't know. It'd be like in science. If you didn't know when t is equal to 0 was, fine. So now let's come back to the shielding problem. Okay? So remember we had from the resistivity, without any resistor in there, we got this. With the resistor, got completely shielded. And we said, well, that's a problem. But now we're going to do inductive source. So how would we expect that to react? Peter? When we were doing the inductive source, and we did the layer, and then we had we put a resistor in it. What was the effect of the resistor?
What to do to avoid avoid the body? Where to just the form to avoid the body?
It may be.
Almost no current inside the resistor, but in this case we got current below the
Right,
resistor.
yeah, so we had this layered model, we put a resistor in it, and then we looked at the currents, and there were still currents above, there were lots of currents below, but there was just no currents in the resistor. In other words, and then we looked at the value of the sounding, like with the resistive layer, without the resistive layer, no difference. So the resistive layer is transparent, so it doesn't hurt us. So we should now expect, therefore, that this problem should be overcome. So if we look at a thin resistive layer up here, so without any resistive layer, that's what we see. So these are the currents that are obtained. If we put in a thin resistive layer over top, see the same thing. And here's what we had with just the resistor. So this is great, right? In fact, this is really good, right? Because we had DC resistivity, which we thought the microphone is. We had a DC resistivity this way. We had DC resistivity, which looked like, wow, this is a really good survey. And then realized like, oh, put in resistive layer, we're moved. Yeah. Okay. But now we come along and we have an entirely different type of physical phenomena. We're going to induce currents. And we find that, oh, it's just simply not affected by resistors. So it's fine. So if we're trying to find this body beneath the resistive layer, we just want to use an inductive source. Now we're good to go.
What if the layer is conductive instead of resistive?
Okay, good question.
Gonna be like the opposite of the DC case. In this case, with the conductive, you won't be able to see anything. That's it.
Perfect. So with the conductive, pardon me? Yeah, so with the for the DC with the conductive layer, okay, then we didn't see anything because everything got channeled through. Okay, so it just short circuits through. If we use our EM system, the inductive system, here it is without any conductor. If we put the conductor in, it's basically all in that zone, and we're basically shielding the sphere. And yeah, here's what we have if we just have the conductor. If we look at the effect, so this is the sphere, so this is this one. Okay, so the solid line here is the sounding just over the sphere, and these X's over here is the sphere plus the conductor comes up here, or the kind of the dashed lines in here is just the conductor. You see, you can't see any difference with just the conductor or putting a sphere. So you're still moving, right? Unless, of course, you want to find a conductor. But, you know, so the inductive part sees conductors. The resistive part is very sensitive to strong resistors. And, you know, if you're trying to see through something that's very conductive, you might just not be able to see through. The only way that you can do it is if you have, you know, low enough frequencies so that your skin depth through whatever medium you got is still long enough. Yeah, so then there's another app, vertical magnetic dipole over a sphere with overburden. So I think that's probably a perfect place to leave that. I think we should go for lunch. Then we'll come back and then we'll just kind of refresh things a little bit by walking through, a couple of apps, and then we'll start back again with case. Okay. 11:59. So are we going to the same place we did yesterday for lunch, or what's our plan?
Uma semana,
A gente pode ir lá tomando uma.
ou pai.
Chega lá no meio, a gente pode ir no
Vou já para aquecer.
Amanhã, gente. Pode ir poder, a gente vai.
Pode usar, cara.
Amanhã não estou. Amanhã vai ser foda.
Aqui, hoje já vai ir casa, né?
É, não é naquela